This window looks like glass, but it doesn't sound like it when I tap my finger on it. What is it? What am I looking at?
Come on, you guys, go! Let's do it! Come on and do, 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 come on and do,
I am Carol.
I'm Jim. I'm Aaron.
Do you know what is the windows made of?
Glass.
Right, I'm pretty sure you have seen the glass before. The windows at home, the screens of the phones, laptops and TVs, some containers, jewelry, and much more. They are all made up of by the glass. Do you know what is the glass is?
It's a transparent and fragile substance.
Sometimes. There is a scientific definition of the glass. Glass is a non-crystalline substance. That means its molecules are not arranged in a specific and regular pattern. Window glass is made up of chemical compound called silicon dioxide, the major component of sand. Believe it or not, glass is made from a liquid state. When you heat the sand until a credible high temperature, about 1700 Celsius, and then you can shape it when it cools down. And using different process can give you a different types of the glass.
But what about airplane windows? Won't they shatter?
Oh, actually, they're a different type of glass. It is a polymer called polymethyl methacrylate. It is much more resistant to the scattering.
Cool. It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day for this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I've always wanted to have a neighbor just like you. Always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, we might as well say, would you be mine? Could you be mine? Would you be my neighbor? Hello there, neighbor. Today we're going to talk about polymers. Now, a polymer is like a group of friends, and a monomer is like the individual person making up that group of friends. Now, monomers, they're lonely. They just kind of float along, but every now and then, two monomers will meet up, and then they'll want to hold hands. We call this polymerization. Now, those two monomers, now friends, will meet up with another monomer, and then they'll hold hands too. And eventually, you'll get a big group of monomers, and that's what we call a polymer. Now let's have some make-believe. Trolley, there's our good friend Trolley. Trolley's gonna take us to the land of make-believe, where molecules are huge.
I like you. I like you too. Let's be friends.
Let's be friends too.
I want to be friends too.
I like you.
I'm the last one. Yay! We're a
We
polymer.
are polymer.
Yeah, we're a polymer. Polymer. Carol.
Hi, welcome to Carol's Lab. Have you ever left a bucket outside in wintertime and find it cracks more easily than summertime? This phenomenon is called glass transition. It is a unique characteristic of polymers. There is a certain temperature called glass transition temperature. Polymer below the glass transition temperature is very hard and brittle. When you heat it above this temperature and the molecules are tangled enough, it turns into a rubbery state. Let's take a look at the glass transition with polystyrene in the packing peanuts.
Hey Carol, what's up?
We were just about to do a cool science experiment. Wanna come check it out?
Oh, over there. Let's go check out.
Hey, so we're going to be looking at the glass transition of polystyrene. So you've seen this, it makes up your cups and whatnot. So we're just going to heat it up until it melts. See, right now the polystyrene is in a glassy state. So you notice how it's hard and rigid? Now the air bubbles make it look like it's kind of bouncy, but it's actually a solid right now. Definitely a glass. So what we're going to do is we're going to melt it and we're going to watch the phase transition. Alright, so we're going to turn on our hot plate real quick to about 100 degrees Celsius, because that's about where the glass transition of polystyrene is.
Okay, so what we're left with now, after heating up the polystyrene, is these small chunks, because all the air has escaped out from the heating. As you can see, they're very easy to mold, very easy to push around, like in a very kind of rubbery-like state. So once these start to cool down again, you'll see they'll get harder. And so let's let them sit for a few seconds.
One eternity later.
Alright, we're back. As you can see, the polystyrene has cooled down once again below its glass transition and is now much harder and is back in its glassy state. Rheology.
Butterfly in the sky, I can go twice as high. Take a look, it's in a book.
Rheology.
Rainbow, I can go anywhere. Friends to know and ways to grow.
Rheology.
Rainbow, I can be anything. Take a look, it's in a book.
Rheology.
Rainbow,
Rheology.
rainbow.
you a story today about polymers and their glass transition temperature, and some of the weird things that kind of go along with that.
If you give polystyrene a benzene, its phenyl groups will want to interact. If its phenyl groups interact, it will probably want to mix. If the polystyrene and the benzene mix, the polymer chains will have to spread out. If the polymer chains have to spread out, the free volume will probably increase. If the free volume increases, the polymer chains will want to move around. If the polymer chains want to move around, they will no longer be glassy. If you want the polystyrene to be glassy, you will need to cool it down. If you cool the polystyrene down, its free volume will also go down. If its free volume goes down enough, it will be glassy again.
Oh, hi there. Welcome to my kitchen. So today we're cooking us up some polymers. Now, while this batch is going, and it's going to be a little while, we're going to pull up some ones that I made earlier today. Now you can see that these have pulled down. Alright, so here are our polymer chains. You can see they're long, they're interconnected, and right now they're really tangled up and chaotic. Now between them you see there's not a lot of space. That space in between them we call the free volume. And as you can imagine, and you can see right here, when there's not a lot of space, it's really hard to move it around. They like to hold on to each other. So right now this is in a glassy state since there's not really much free volume and they can't move without the other ones moving. Alright, so now we're going to come over here to our faucet and we're going to add some free volume. Alright, oh yeah. Looking tasty. So as you can see, as we keep adding more and more free volume, there's more space between all of our polymer chains. And as there's more space, they move a lot more easily. And so now, they no longer have to interact with each other as strongly to be able to move. So right here, we're no longer in a glassy state. Our polymers are able to move semi-independently and just have a lot of space, which is really good. Free volume.
Darn, lost again.
Yeah, I'm sorry, Jim. So, you know what this kind of reminds me of?
What's that?
The lattice model of entropy in a polymer.
What's the lattice model of entropy in a polymer?
Well, I'm glad you asked that, Jim. Let me go and start off with what entropy is.
So now, whenever we talk about entropy, what we're talking about is a measure of the number of possibilities there are in a certain system or the chaos of the system. So in the case of our Connect 4 board or our little lattice we have, the more possibilities, or the greater the number of ways that we can arrange the pucks, the higher the entropy is. And the opposite's also true. If there's fewer ways to arrange them, then the lower the entropy is. So this is simple whenever we're talking about just individual pucks and they are constrained to very specific locations. But whenever we start talking about polymers, it gets a little bit more challenging. Because when you have a polymer, it's not just taking up an individual location. It's taking up a large number of locations. So what the lattice model does is we say each monomer is its own entity, but then we constrain it so that it's got to be within vicinity of its neighbor. And what we find is that this actually lowers the number of possibilities because there's more constraint on the system. And because it does this, it lowers the entropy. So as you polymerize, you actually lower the entropy. And as you go to a smaller length of a polymer, you increase the entropy. Now, the entropy of a system is also useful whenever we start talking about the glass transition temperature. And the reason for this is that entropy affects mobility. If you have a higher entropy, there's a greater number of possibilities for the polymer to move. And if the entropy is lower, then there's fewer ways that it can move. And if there's fewer ways it can move, it makes it more stiff and it puts it into a glassy state. So therefore, if we take a system with more entropy, then it's not going to favor being in a glassy state quite as much as one with a lower entropy, because then with a lower entropy is going to have a harder time moving out of that glassy state.
So I was right. It is a glass. But not the glass I was thinking of. It's a different, polymeric glass. Cool.
This is polymer polyester. This is polymer low density polyethylene. This is polymer high density polyethylene. And this is polymer polystyrene. Yes, that's right. No, that's the wrong.
You gotta talk louder than that, seriously.
Okay,
like
okay.
like this. Talk like this. I don't care if the words are wrong.
Okay, cool.
When am I supposed to come in? Which part? Oh, you're filming.
Oh, hi there. I'm not LeVar Burton, but I'm going to read you a story today about the...